So welcome to the video. Today we're going to take a look at how to do a paired samples t-test on version 31 of SPSS. So for this video, we're going to take data from a real world intervention intended to improve the algebra abilities of children. So in this left column, we have the children's scores on an algebra test before the intervention, and we have the children's scores on an algebra test after the intervention. So we're going to use this paired samples t-test to investigate whether there's a significant difference between the algebra scores before the intervention and the algebra scores after the intervention. So the first thing we're going to do is go down to variable view. Next, we're going to go to the top row in this name column, and we're going to give a name to one of the levels of the independent variable. So let's enter pre-underscore intervention. And I'm using an underscore in this name because SPSS won't allow us to use a space. So then I'll enter the name of the other level of the independent variable. So let's call this post underscore intervention. Once we've done that, we can tell SPSS that our dependent variable is a continuous variable, which is otherwise known as a scale variable. So we'll select scale in both of these rows. Then we can go over to data view, and we can see that pre-intervention and post-intervention appear at the top of these two columns. So then we can just copy and paste our data from the Excel spreadsheet into SPSS. So I'll select the top left cell, and then I'll scroll down to the bottom. I'll find the bottom right cell, and whilst pressing Shift, I'll select that cell to select all of the data. Then I'll go to Command or Control C to copy those data, and then I'll go back to SPSS and I'll choose the top left cell. And you can either go to Command or Control V to paste the data in, or you can go to Edit and then paste. So one of the assumptions of this test is that the differences between the two levels of the independent variable are normally distributed. So to test this assumption, we actually have to create an additional variable that represents the differences between these two scores or between these two columns. So to do this, we can go up to transform, then down to compute variable, and we can give a name to this new variable that we're going to create. So I'm going to call this difference, and then I'll transfer my pre-intervention variable over to this box using this arrow, and I'll click this minus button, and then I'll transfer post-intervention over, and then I'll go to OK. And now we can see that we have a variable that represents the differences between these two columns. So we have a 3 here and a 6 here. Therefore, we have a -3 here. We have a 6 here and a 5 here. Therefore, we have a 1 here, etc. So now we can do a normality test to see whether these values are normally distributed. So to do this, I'm going to go up to Analyze and then down to Descriptive Statistics, then over to Explore, and then I'm going to transfer Difference to this dependent list. Then I'll go to Plots. I'm going to untick stem relief, but I will tick histogram, and I will tick normality plots with tests. Then I'll go to Continue, and then I'll go to OK. And then I'm going to look at this test of normality table, and I'm going to focus on the Shapiro-Wilk side of it. And we can see here that we have a value of less than 0.001. And as this is less than 0.05, it indicates that our data are not normally distributed. So this assumption of the test has been violated. In this case, I would probably switch to using a non-parametric version of this test, such as the Wilcoxon test. However, for this example, I'm just going to ignore the fact that this indicates that the data are not normally distributed, and we'll just continue with running the analysis. So to do this, we can go up to Analyze, and then down to Compare Means and Proportions, and then we'll go over to Paired Samples t-test. We'll then transfer one level of our independent variable to this variable 1 slot. So we'll select that there, we'll press this button, this arrow button, and then we'll select the other one, and then we'll transfer that over with the arrow button as well. We can see we have estimate effect sizes selected here. That's good. So we can just go to OK, and that's going to run the test for us. Before taking a look at those results, I'm just going to show you how to create a graph to represent the data. So to do this, we can go up to Graphs, and then we can go down to Charts Builder. If this comes up, we can just ignore it by going to OK. And I'm going to double click on this simple bar option. I'm then going to transfer one level of the independent variable to this y-axis box, and then I'll transfer the other level to the same box. That will open this dialog box. We can just close that by going to OK, and we can tell SPSS that we want to have error bars on our graph. So if we tick display error bars here, and I'm going to leave this as it is. We have a few different options, but I'm going to choose for my error bars to represent 95% confidence intervals. So once this looks like this, we can go to OK, and that's going to generate this bar graph for us. If we want to edit it, we can double click it to open the chart editor. We can click on any elements within the graph to edit those. For example, if we double click this, we can remove the underscore between those two words. We can also select any bits of text and then change the font style using this menu, and we can change the font size using this other menu. We can also change the size and color of the bars. For example, if we go to bar options, we can move this thing to the left to have some thinner bars. And if we go over to fill and border, we can use a different color. Normally we use a gray color in APA style. And then we can just close this, and any changes will be saved automatically in this output file. So that's how to create a graph. Let's now take a look at how to interpret the results of the paired samples t-test. So the first thing I'm going to look at actually is this paired sample statistics table, and at this mean column, where we can see that we have a pre-intervention score of 3.32 rounded to 2 decimal places, and we have a post-intervention score of 5.15 rounded to 2 decimal places. So this indicates that the algebra scores of the children were higher after the intervention compared to before the intervention. But we need to look at the paired samples test table to determine whether that difference was significant. So specifically, I'm going to look at this one-sided p column within the table where we have a p-value of less than 0.001, and as this is less than 0.05, it indicates that there was a significant difference between the pre-intervention scores and the post-intervention scores. And I'm focusing on this one-sided p column based on the assumption that we had a one-sided or directional hypothesis. So a directional or one-sided hypothesis is something like, it was hypothesized that post-intervention algebra scores would be significantly higher than pre-intervention algebra scores. So it's something quite specific. On the other hand, if we had a non-directional or two-sided hypothesis, we would look at this two-sided p column instead. So in this case, a non-directional hypothesis would be something like, it was predicted that there would be a difference between the pre and post intervention algebra scores. So we're not saying which is going to be higher. So that's essentially how we interpret the results of this paired t-test. But let's take a look at how to report the results. So I have this example here, and I've said a paired t-test was conducted to compare algebra scores before and after the intervention. I've said that a Shapiro-Wilk test indicated that the differences between the time points were not normally distributed, and then I've entered these stats here. As I mentioned before, if I found that these differences were not normally distributed, in reality I would have switched to using a non-parametric test instead, but as this is just a tutorial, I'm going to continue with the paired samples t-test. So let's take a look at where these stats come from. So we have a value of W equals 0.96, and that's what we have here. We have a degrees of freedom value of 167, and that's what we have here in the DF column. And we have a sig value of less than 0.001, and that's what we have here. So I've said that scores were significantly higher after the intervention compared to before, and then I've inserted all of the stats. So the first stats I've reported are descriptives. So we've got the means and standard deviations. So if we scroll down, we get to this paired sample statistics table, and we can see that we have a mean of 3.32 in the pre-intervention group and a mean of 5.15 in the post-intervention group if we're rounding to 2 decimal places. And that's what we have here and here. And we have a standard deviation of 1.20 for after the intervention and a standard deviation of 1.65 before the intervention. And those are the values that we have here in the standard deviation column of this table. So next we have the results of the t-test itself. So we have t equals minus 14.24, and that's coming from this paired samples test table. We have this t column here and a value of minus 14.24 rounded to 2 decimal places. And we have this degrees of freedom value of 166, which is what we have in brackets here. And we have this p-value of less than 0.001, which is what we have here in the one-sided p-value column within this table. Lastly, I've said that the effect size was large, and I've said that Cohen's d was 1.10, and I'm getting that from this paired samples effect sizes table. And specifically, I'm looking at this Cohen's d row and at this point estimates column, where we have a value of minus 1.102, which is just rounded to minus 1.10, and that's what we have here. And I'm saying that this represents a large effect, and that's based on these criteria we have here, which say that values between 0 and 0.2 represent very small effects, those between 0.2 and 0.5 represent small effects, those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. Of course, 1.10 is further from 0 than 0.8, which is why I've described this as a large effect. So that's essentially it for the paired t-test on SPSS. If you have any questions, let me know in the comments and I'll try to get back to you. Thanks for watching, and I'll see you next time.